All right. Hi, everyone. I'm Hussni Chahadeh, and this is my presentation of Professor Leon Cohen's paper called The History of Noise, which he wrote in 2005 on its 100th anniversary. Noise. Despite it being considered unwanted or requires filtering, noise has had a profound impact on various fields. From its inception a century ago, noise influenced every area of science, but its history is often misunderstood or distorted. Its story is fascinating, and understanding its true historical development is important. The concept of noise emerged swiftly and powerfully, transforming science and our understanding of matter, and played a crucial role in settling the debate about the existence of atoms. While it's argued that learning history is essential to avoid repeating past mistakes, this notion is not entirely accurate. However, science history is a totally different story. It's exciting, inspiring, and an excellent way to learn science. In the field of noise, for instance, reading the original papers of scientists like Paul Langevin or Leonard Ornstein can be more enlightening than reading modern books on the subject. And especially the ones of Albert Einstein, who is well known for his simple, straightforward writings. And of course, he is mainly known for his theories of relativity, but among his endless contributions were the ones to statistical mechanics, especially the study of noise. One of his noteworthy accomplishments in this area was his work on Brownian motion, which is a type of random motion observed in particles suspended in a fluid, resulting from their collision with the fast atoms or molecules. In 1905, the same year he proposed the special theory of relativity, Einstein developed a statistical molecular theory of liquids that explained this random motion, validating the atomic theory upon which statistical mechanics is based. This understanding of noise has had far-reaching implications, impacting fields as diverse as electronics, finance, and biology. 1905 is known as the miracle year of Einstein's. The three miracles he introduced were Brownian motion, where he aimed to prove the existence of atoms. The second was the explanation of the photoelectric effect, where he introduced the idea of photons and setting the stage for quantum mechanics, and the special theory of relativity, transforming our understanding of space and time and revealing that energy and mass can be converted into one another. Our part of interest today is Brownian motion. This phenomenon was first observed by the botanist Robert Brown in 1827, who noted that the erratic movements of pull-in particles in water under a microscope. You can see on the right here a real microscopic view of pull-ins moving. Here, this, I think, an exact view of what Brown saw. And Brownian motion today is a fundamental concept in many fields, including physics, chemistry, mathematical finance, and even population genetics. Despite the intuition one would have from its name, Brown did not discover Brownian motion. However, he studied it seriously, systematically, exhaustively, and passionately. Brownian motion was discovered in the early days of the invention of microscope. Many thought that these erratic movements were possibly due to some primitive life force. The debate over the existence of atoms ranks among the top scientific debates. Democritus, a Greek philosopher, is often credited with the idea of atoms, but his ideas were not based on scientific reasoning. Bernoulli, however, provided a scientific basis for atoms by explaining Paul's law. Avogadro proposed that a gas is the same for all substances in a fixed volume, regardless of mass, size, or nature. This led him to discover his number, although it was not taken seriously during Avogadro's lifetime and was not named until much later. Einstein aimed to find a measurable experimental manifestation of atoms and predicted a microscopic observable fact. he introduced a fundamental stochastic argument and derived the probability distribution for small particles, leading to the well-known equation for diffusion. Then, from that, he walked his way until he ended up finding a formula for Avogadro's number. This approach demonstrated how a stochastic phenomena could be used to measure deterministic numbers in science. In the light of all of this, Einstein saw that the heavy particle was just a big atom pushed around by real atoms. And according to energy equipartition, that the statistical properties of the big particle are the same as the real invisible atoms. Therefore, we can use the heavy particle as a probe of the ones we can't see. In 1908, Paul Langevin wrote a paper which aimed to derive Einstein's result in a more physically transparent way that also simplifies the mathematics. Langevin's approach was to use Newton's equations, which is direct if you know the forces. This was the first time in history that Newton's equations were used with a random force. Albert Einstein and Paul Langevin both made significant contributions, but they were not directly involved in determining the value. And contrary to what is frequently stated, Perrin did not verify Einstein. Prior to Einstein's work, Perrin was focused on atoms and the measurement of Avogadro's number. He was the one who identified its exact value and won for that the Nobel Prize in 1926. Thus, while Einstein and Langevin did not specifically determine Avogadro's number, their work on Brownian motion created the necessary framework, theoretical framework, that eventually allowed other scientists to conduct experiments that yielded a value for Avogadro's number. One of the biggest technological changes that our world has faced was the invention of vacuum tubes. Noise became of importance in electrical engineering because of this device. And subsequently, the importance of noise rose to its highest levels. Magnetism, electricity, and understanding the relation between them was seen as one of the biggest challenges for the intellectual minds at that time. It was Maxwell who brought their understanding into comprehensible formulas, which today we call Maxwell's equations. However, these equations were expressed in a way that was hard to be dealt with, and it was Oliver Heaviside who came up with a simplification for them, which we know and use today. The topic of electromagnetism was among the hottest during that period, where engineers were split between supporters, so-called Maxwellians, and antagonists. Many of the world's problems back then were solved by the supporters, even though most of the engineering medium were up against the concept of electromagnetism. Electricity and its applications advanced in an accelerating way. Edison discovered that a heated metal generates electricity. And his electric light bulb lighted up the world with many of his latter inventions. Electricity was the technology of the 20th century, and inventions related to it came up naturally, like the light bulb, which required the invention of electric generators to provide it with energy. Namely, two types of generators were invented, the DC, which was invented by Edison also, and the AC generator, which was a cooperation of both Tesla and Westinghouse. The vacuum tube, which is considered the greatest invention, as we said, came up later to make worldwide communication a reality and led to the invention of the radio. It also started in 1904 with Fleming, who invented the vacuum diode, which was created initially as an AC to DC converter. It was later developed by De Forest in 1905, where he added a metal grid to the middle of the device, as you can see on the right here, in order to charge it according to the desired speed that he wanted the electrons to be emitted by inside the tube, making the current flow inside it proportional with the potential of the grid, where small variations in the grid's potential will result in massive changes in current flow. At that period, the vacuum tube became the most important device in the markets until it was replaced by its successor, the transistor. Noise played a crucial role in the development and understanding of vacuum tubes and semiconductor devices in general. The behavior of additive noise on amplitude modulation and frequency modulation, two methods of radio transmission, which came to existence because of the vacuum tubes, was essential to understanding which method is less sensitive to noise. And modern communication theory, which is based on stochastic processes, incorporates probabilistic considerations in transmitting information, as we actually study in our digital communication class here. In electrical engineering, there are two types of noise that we observe. Thermal noise, that is caused by the thermal agitation of charge carriers, usually electrons, in an electric conductor, and shot noise. Let's explain it as when the current is low enough that individual electrons can be counted through a cross-section, the randomness in their arrival causes a fluctuation in the current. That's basically shot noise. Walter Schottky, a physicist with wide-ranging contributions, is often incorrectly credited solely with the discovery of shot noise, while Johnson is credited with thermal noise. Schottky's 1918 paper actually considered both types of noise. Johnson also clarified many issues regarding both shot and thermal noise. He worked closely with Harry Nyquist at Bell Laboratories and both published influential papers on thermal noise in 1928. Quantum mechanics, an inherently probabilistic theory, has produced a new kind of noise called quantum noise, which has significantly contributed to the development of noise theory and its applications. The applications of quantum mechanics have become more important since the invention of lasers, masers, and the field of quantum optics. The invention of the laser intensified the examination of quantum noise with researchers using different approaches to understand the laser's bandwidth. There remain many unsolved issues also in quantum noise, such as obtaining a proper quantum mechanical Langevin equation or defining autocorrelation functions for operators. So to conclude what I just explained about the paper, it provided an overview of the development and understanding of noise in various scientific fields. The paper discusses the historical context, key discoveries, and theories related to noise, starting from the early days of thermodynamics. And also the paper covers different types of noise, such as thermal noise, shot noise, quantum noise, as well as the contributions of prominent researchers. It also highlights the role of quantum mechanics in noise theory and its applications, with a focus on the study of quantum noise in relation to the development of masers, lasers, and the field of quantum optics. And thanks a lot. That was all.
Hussni, good job. Did you make any changes in the presentation?